And so we start the second week. We repeated the basic definitions of the previous week. And today, Antoine Ducros will talk about Étale cohomology of analytic spaces.
Okay, so Étale cohomology. So let me begin by some general motivations about Étale cohomology. So I will speak about Étale cohomology of schemes and of analytic spaces. And in both cases, I mean for schemes and for analytic spaces, Étale cohomology is a general cohomology theory which behaves like classical cohomology theory. I mean singular cohomology of complex analytic spaces, as an example. So Étale cohomology is a theory which behaves like classical, say, for example, singular cohomology of complex analytic spaces. And in fact, such cohomology was needed for two reasons. I mean, there was a good reason to develop such a cohomology for schemes, and another one to develop it for analytic spaces. So, such a cohomology was needed. So, for schemes, in order to prove the Weil conjectures, one needed such a cohomology to be applied to varieties, algebraic varieties of our finite fields, so to be applied to algebraic varieties of our finite fields. And for analytic spaces, such a cohomology was needed for Langland's program. It was needed for Langland's program. I will not give a lot of precisions about it, but in this context, it has to be applied not to algebraic varieties, but to some analytic spaces, which are analogous of Poincaré upper half plane, and especially so to be applied to analytic spaces like the p-adic upper half plane. What is this guy? So it's you just take P1 over the Berkovich analytification of P1 over QP. That is a compact Berkovich analytic curve. And then you remove a compact subset. So you will get an open subset, which will be itself an analytic space. The compact subset you remove is just the set of QP points, classical QP points of it, which is compact, because QP is a locally compact field. And so the cohomology of such an object was supposed to play a very important role in Langland's program. But first of all, one need to be able to define such a cohomology. And so Étale cohomology for schemes was developed by Grothendieck and all the school, and for analytic spaces it was developed by Berkovich. So let me now make some remarks about such cohomology. So if one wants a cohomology which behaves like the classical ones, the usual, the first idea could be to use the Zariski cohomology for schemes and the classical topological cohomology for Berkovich spaces, but it doesn't work at all, as an example, because of dimension reasons. So, first remark. if X is a scheme or a Berkovich space of dimension D, topological cohomology. It's a topological space, so it comes with a cohomology theory. Topology called cohomology of X vanishes in rank greater or equal than D plus 1. And so if one wants a cohomological theory which behaves classically, one should have here 2D plus 1 and not D. Because, of course, a complex algebraic variety of dimension D can have a cohomology up to rank 2D and not D. So it cannot play the role of a classical cohomology theory. That's the first remark, just for dimensions reason. And the second remark was due to Serre. I will just explain because I find that it's quite nice remark. Second remark, which was due to Serre. It is impossible to define a scheme theoretic cohomology which behaving like a singular cohomology and with values as an example, with value in Q vector spaces. You can define a singular cohomology with coefficient in Z or in any ring or in Q. It's especially useful. But it's not possible to have such a scheme theoretic cohomology behaving like singular cohomology and providing Q vector spaces. Why is it impossible? Because of the following fact. The fact fix P a prime number, Fp bar an algebraic closure of the field with P elements, and so there exists an elliptic curve E over Fp bar whose ring is such that if you look at the ring of endomorphism of E is an algebraic group, so it has a structure of ring on its set of endomorphisms. So that end of E, you tensor it with Q, and what you get, usually in the case of an elliptic curve over C, you can get either Q or either a quadratic number field. Here you can get something else. Is a non-commutative field with center Q of dimension 4. It can also be called a non-trivial Q quaternion algebra with reference to the usual quaternions. So it exists such a curve. And now assume that we have a good cohomology theory but with values in Q vector spaces. Now assume there is a good cohomology theory with values in Q vector spaces. Then one should have, as for any honest elliptic curve, then one should have H1 of U being isomorphic to Q2. two-dimensional spaces over Q. And the action of the ring of endomorphism on the elliptic curve on the H1 vector space would be compatible with the group structure on E. Then we would have a map, a morphism from end of E to GL2 of Q just by acting, and this morphism will induce one like this, end of U tensor Q. You will have such an arrow, but this is completely impossible because it's a non-commutative field. So any morphism from here to a non-zero ring is injective. Both have the same dimensions. That is, so M2 of Q, sorry, M2 of Q. Both have the same dimensions, and they are not isomorphic, of course, because it's not a field. So it's impossible. Impossible because it is a field, non-commutative field of dimension 4, and it is of dimension 4. So it's not possible to hope for general cohomology theory in a purely algebraic settings, taking its value in Q vector spaces. That's the reason why when you have already heard about Étale cohomology, you maybe have heard about Étale cohomology with torsion coefficients, or Étale cohomology with L-adic coefficients, but never about Étale cohomology with Q coefficients. It's possible to define it, but it will not give us it will not give the expected results. So one never uses it. Yes?
What are the axioms exactly of your good cohomology theory that involve H1Ds and Q2?
I don't know exactly. It's a general list of axioms, which those are called the veil cohomology. I cannot give here. I cannot give here the precise. But what you expect is that for usual algebraic variety, as well in characteristic P as in characteristic 0, it gives the Betti number you expect, especially for abelian varieties and for And you, as an example, you also want the H2 of a smooth curve to be just one-dimensional and so on. So now let me. I will now go to the general. To the technical ideas about construction of Étale cohomology. But before that, I will give very general, I will present a very general construction, which is the general idea of a growth-ending topology. So in general topology, usually when general topology uses axioms about open subsets. In a growth-ending topology, well, the idea is to axiomatize not especially open subsets or even any subset, but just the notion of covering, or covering family. So one starts from the following datum. Let's see the category. So it means that one has objects and arrows, and you can compose the arrow. You have identity maps. Like, okay. And I will assume that C has fiber products. I will explain what it is and give some example. Assume C has fiber products, X times Y, Z. What does it mean? So it means that let X and Z, Z, G, Y be two maps, be two arrows in the category. What do we call a fiber product of X and Y of X and Z over Y with respect to F and G? It's a general, so a fiber product say T of X and Z over Y is an object. So T equipped with true arrows, which one usually called projections. T, so you are to X, T to Z, your Q and P. So here it's F and G, so such that this diagram is commutative. F composed with P is G composed with Q, so that this diagram is commutative, and which is universal for these properties, that is, and such that every time you have a commutative diagram like that one, there is a unique arrow. So you have a commutative diagram like it, like this. Then there exists a unique arrow, T of S, making everything commute. Sorry? From S to T, sorry. S to T, making everything commute. So it's just, so it's an object defined by a universal property, so it does not necessarily exist, but when it does, then it is unique, up to canonical isomorphism. So, and so let me just give some examples of fiber products in different categories. So it's unique, it's canonical when it does exist. And so let me give a few examples of fiber products in several categories. So if C is the category of sets, then the fiber product is just the usual set theoretic fiber product. So X, Y, E, Y, Z is just the set of X, Z, such that f of X equals G of Z. G of Z is the usual set theoretic fiber product. If C is the category of topological spaces, it's the same. But you have to define it not only as a set, but as a topological space. So it's the same, equipped with the product topology. You take this set, but you render it with the product topology, coming from the topology and X and the topology of Z. If C is the category, say, of schemes, I will not give the general construction of the fiber product, which is not very pleasant, just what happens in the affine case. So what you have is that spec A times spec B, spec C is just the spectrum of A tensor B, C. And you have the same phenomenon in analytic spaces. I will just say what happened in the phenoid case. So M of A times M of B, M of C is nothing but M of A tensor over BC. But here you have to take the complete tensor product. So those are 4 examples of categories in which you can build a fiber product of 2 objects over a third one. It's not possible in a general category, but in this example it's possible. And so, to define a Grothendieck topology, I will assume that I'm working on a category in which such objects exist. So, now, Oh, I will maybe give a last example because it will, if one wants to see the link between the general Grothendieck topology and the classical topology on a topological space, it's useful to think about this example. So X is a topological space. C is the category of all open subsets of X. And the map are only the inclusion, with inclusions as maps. Then Y cross any few subset of V of W, and V is a subset of W. All are open subsets, and U cross WV is just the intersection. So here it's very, very simple. And so now, let us go back to see a general category with fiber products. I will define what is a topology on C. In fact, technically, it's just what one calls a pre-topology because there is a quite more general notion of a Grothendieck topology, but I don't want to speak about it. So here I will call it simply a topology. So say with fiber products. C with fiber products. A topology on C consists in the following data. For every object X of C, some families of morphisms xy to X, indexed by some set Y, are distinguished and are said to be a covering of X. Distinguished and are said to be a covering of X. And one has to, the following axioms has to be satisfied. So it's just a purely categorical theoretic notion. For every object, you consider all possible families of maps going from some object of X of C to the original object, and you decide that some of those families, you decide to call some of those families covering of X, and you have to respect the following axioms. Have to be fulfilled. So as you will see, those axioms are very natural if you think to usual coverings of topological space by open subsets as an example. Following axiom, so if Y to X is an isomorphism, then it is a covering, First, if Xi to X is a covering, and Y to X any row, then Xi times Xy to Y is a covering of Y. So it behaves well with respect to fiber products. That's for this. Simply for writing this axiom, I needed the existence of a fiber product. And third, if Xy to X is a covering, and if, say, Yj to Xi indexed by j is a covering for every I, then I can forget the Xi's, and then Yj to X with two indices now, Y and J, is a covering. So we will see when I will give the definition of Étale morphisms, we will see a non-trivial example of such a topology. At the moment, the only example I can give is the example of the classical topology. So example. But of course, for such an example, one doesn't need really all that stuff. But example, the category of open subsets of a topological space with the usual notion of a covering. But there are plenty of other examples, and you don't need in the case of the category of open subset of a topological space is really a set theoretic quadratic topology. I mean that objects are a subset of a big object, and coverings are classical set theoretic coverings. That's the same about the topology that Temkin spoke about. That is the admissible topology on a Berkovich space with the notion of analytic domain and so on. It's also a Grothendieck topology, which is also quite set theoretic, but we will see a little bit later a less trivial example of a Grothendieck topology, which will be the Étale topology. But before defining it, I will explain how one can define sheaves and cohomology of a sheaf on a category equipped with such a topology. So it's called a site category with such a topology, but I will not use this word, I think, during the. But if you see it in a book or something like that, it's what one calls a site. It's a category equipped with a Grothendieck topology. So what is a sheaf on such a category? We mimic the usual definition of a sheaf on a topological space. So, if C, a pre-sheaf, so first of all, one defines a pre-sheaf on C is just a contravariant functor from C, say, to the category of sets. It can be, if you say a sheaf of a pre-sheaf of abelian groups, it will be to the category of abelian groups and so on, from C to set. That is pre-sheaf F. That is that f of u, f of x is a set for every x belonging to C, and every row y to x gives rise to what one calls a restriction map, thinking, of course, of the topological picture, gives rise to a restriction map f of x to f of y, and functor means, so contravariant means that the row goes here, that the rows go the wrong way, and functor means that it behaves well with respect to composition. Everything behaves like one wants it to behave. Okay, so that's just a pre-sheaf, very, very elementary definition. And now, a pre-sheaf F on C is said to be a sheaf if for every x in C, for every covering xy to x of x, so covering in the sense of the Grothendieck topology, and every family Si with Si belonging to f of xi, and such that for every I and G, the restrictions of Si and Sj to xi times x xg. This is equipped with two arrows, one with xi, one with xg. So you can restrict the size. And a priori, you get two different elements of f of that, but they have to coincide to f of that coincide. So, and every family such that coincide, there exists a unique S belonging to f of x such that the restriction of S to xi is equal to Si for every I. So it's just exactly like the usual Schiff conditions. The only difference is that it's not a covering, a set theoretic covering. It's an abstract family of arrows which we decide to call a covering. And you have to replace the intersection by the fiber product. Just because you need an object which you can send on xi and on xg, and which is quite universal for that. And it is the fiber product. But it's the same condition. You choose a family of element on f on xi. You want when you pick two of those elements, you want their restrictions to the fiber product to coincide. Then there is a global element from which everything comes. And this global element has to be unique. That's the definition of a Schiff. So again, for the moment, the first example I just mentioned is a classical Schiff in topology. We will see further in the lecture examples of Schiffs for the Étale topology on a scheme or on a Berkovich analytic space. But for the moment, I just mentioned that the classical Schiffs are part of this theory. So example. Classical Schiffs. So there is the first problem which appears when one makes Schiff, and in fact it's a problem, but it's also what makes the theory very rich and very useful to encode some geometrical phenomena, because it's a phenomenon. In fact, it's a kind of defect of gluing or something like that. So it's a phenomenon which is related to the image of a Schiff. So let F and G be two Schiffs. On C, I mean, and phi, a morphism of Schiffs. I don't write what it is. It's just for every object you have a morphism from f of x to g of x, and it has to be compatible with restrictions. So let phi a map. Then, if you look at the following three Schiffs, you send an object x of C to the set of S in g of x such that S belongs to the image of f of x. It's not a Schiff in general, even in a topological space. It's not because something belongs locally in the image that it belongs globally. The function 1 over z on C star is locally the image of an holomorphic function by the derivation, but not globally. That's the first and basic example. So it's not a Schiff in general. So one defines the image of phi. In some sense, it's the smallest Schiff containing it, or something like that, or Schiff associated with this pre-Schiff. Or the image of phi is a Schiff. In phi is a Schiff defined as x. You send the set of S in G of x, such that there exists a covering xi of x, such that S, I know the restriction like a classical restriction, even if those are not open subsets of a topological space, such that S, the restriction of S to xi comes from f of xi for every I. So what you define as the Schiff theoretic image is not the set of elements coming from the belonging to the image, it's the set of elements which locally belong to the image. Locally with respect to this topology, that is that you have to check it on the covering. And this is a sheaf, which is called the image. And which is, except in very particular cases, it's completely different from that one. As an example, you take the derivation on the sheaf of holomorphic functions on C star, and you look at the image of the sheaf is the whole sheaf of holomorphic function, because every holomorphic function is locally has a primitive. And then, thanks to this, one can define the notion of an exact sequence of sheaves. Now one will need to work with sheaves of abelian groups. Maybe I will write just the example I spoke about. So, example, if F is a sheaf of holomorphic functions on C star, phi from F to F is the derivation, then say D is the derivation, then im D is equal to F, but F of C star to F of C star D is not subjective, is not onto say F1 over Z. So it's a basic example. So now what is let us go back to a general category endowed with a Grothendieck topology. What is an exact sequence of sheaves? So let F, G, H be sheaves of abelian groups. So it's just the same definition as a sheaf, except that it takes value in not only set but in abelian groups, and all restriction maps have to be group homomorphisms. And phi psi 2 morphisms, then 0 F phi G phi C. So, okay, so phi is from F to G and psi is from G to H. 0 is said to be exact. So in fact, the definition is almost what one should expect, except on the right, where this problem of definition of the image appears. So I will just say that it is exact if for every x in C, so there is no, except on the right, there is no problem. So 0, f of x, g of x, h of x, but I don't put any 0 here, is exact. And h is equal to the image, sheaf theoretic image of G, which means that it will not be surjective. Any object here will belong to the image only locally with respect to the Grothendieck topology. At the other point of the sequence, exactness is just usual exactness without any problem related to local phenomena or growing phenomena. But on the right, the condition of surjectivity has to be replaced by the condition that H is the sheaf theoretic image of G.
But this is an epimorphism in the category?
Yes. It's an epimorphism. In fact, the category of sheaves is an abelian category, and there is a general notion of kernel, co-kernels, exact sequence in such a category. So it's not just ad hoc definition, it's part of the general. It is an epimorphism in the category, exactly. It is, in fact, in any abelian category, there is a general notion of the image of a map, and so there is it is so. And so now, if one looks, x is fixed as the functor which sends f to f of x, it is only left exact. That is, when you start from an exact sequence of sheaves, And you look just at the set when one uses the word sections for f of x, so a section of f over x. So when you look at the set of sections of f, g, and h, what you get you get a sequence which is not necessarily exact on the right. That is why one says that such a functor is left exact. And so now, when a functor is left exact, one can define its derived functors. So I will now say a few words about it without giving the constructions, which is so now the general notion of derived functor. Let's now C be an abelian category. Again, I don't want to list all the actions, but it is a category which looks like, say, modules over a ring or something like that. That is that you have zero object, direct sums, the notion of an exact sequence. You can add the morphisms and so on. And especially, so ring over modules, modules over a given ring is an abelian category. The category of sheaves of abelian groups on a category equipped with a Grothendieck topology is also one, so abelian category. So you have a direct sum, you have the notion of exact sequence, and so on. D, another one. And F, from C to D, a left exact functor, which means that every time you start with an exact sequence, you apply F, you get a sequence which is exact, except maybe on the right. Left exact functor, then so a collection of the derived functors, usually denoted by RIF, are defined, are characterized by the following properties. First, R0 of F is nothing but F. 2, every time, to every exact sequence, 0, A prime, A double prime, 0 in C, is associated in a natural way. I mean functorial with respect to all you can imagine in a natural way. A long exact sequence which long exact sequence, so you have a 0. R0 is F, so FA prime, FA double prime, then you make R1 FA, R1 FA prime, R1 F double prime, R2 FA, and so on. Infinite exact sequence in general. And third, this family F is universal for this property. In some sense, I don't want to precise here. So, at the moment, I didn't claim that it exists. In fact, I just wanted that if there is a derived, what we call the derived functors of functor F, is the collection of all those functors, if such a collection exists. So you just have to, you want the R0 to be just the initial functor. You want that the defect of exactness is controlled exactly by those functors. And you want this to be universal in some sense, which is not so pleasant to write, but not very difficult. And fact, such the derived functors always exist as soon as C satisfies some technical conditions which are fulfilled by the shifts, by the category of shifts of abelian groups for a given Grothendieck topology, for a category, on a category equipped with a Grothendieck topology. It means that when you start from the category of abelian groups on a category with a given Grothendieck topology, and as every time you have a left exact functor in this category, you always can derive it in the sense I gave here. And the cohomology associated with this Grothendieck topology will just be the cohomology of a shift, which will just be the derived functor of the functor x on x maps to f of x. So definition. If C is a category equipped with a Grothendieck topology, and if X belongs to C, one denotes by H0 of X F F a sheaf of abelian groups of XF, the group f of x, and by hi of xf, the group, say, how can I say, the group Ri H0 of xf, I mean the yth derived functor of f maps to H0 of xf. So you have a category, you have the notion of shift. You fix an object. When you look at the functors with sensor shift to its section on that object, it is only a left exact functor, which we usually denote by H0, being only a left exact functor in a category in an abelian category which satisfies some technical conditions. It has derived functors. Those derived functors are called the cohomology groups of the shift on that object. So maybe you find it quite not so close to the usual singular cohomology, but the fact is that for reasonable topological spaces, like complex algebraic variety, complex analytic varieties, but in more generally CW complexes or something like that, the usual singular cohomology coincides with that one. Remark: if X is a reasonable topological space, then hi of x q, say hi singular of xq, coincides with hi of xq with the shift theoretic. Just defined. I should maybe say what I mean by Q as a shift. I will not write it, I just say it, because if you look at the functors which sends an open subset of X to Q, it's not a shift in general. So you have to you have to associate to this functor a shift in order to build what one calls the constant shift associated with Q. It's you can see it as if it's a usual topological space, you can see this shift as a shift of locally constant functions from X to Q. Unreasonable topological space.
Very simple example where this
maybe I think I don't know. I think if, as an example, if you take a scheme or something like that, which is topological completely pathological, you have no singular cohomology because you will not probably. I've never thought about it, but I think that if you try to embed a polyhedron into a scheme just in a topological way, probably it's a constant map or something like that. I think so, but. So if you allow some very pathological topology, you certainly can singular cohomology is something which is for which you need that your spaces are not too far from the real line. I think in some sense.
So schemes are not reasonable topological.
No, as topological space, definitely not. They are not separated. They are no. That you know what is a affine line from the topology of the scheme theoretic affine line is just closed subset are just only finite the whole line or finite subset of closed points, and no, that's not from purely topological in a purely topological sense. I don't think that a scheme is a reasonable is not a very pleasant object. Topology of a scheme is quite combinatorial. In fact, it's not so. I don't see a scheme as a... So, an analytic space is in the sense of Berkovich is a more reasonable topological space, and for such a space, it will, it's true. Maybe at least if it's locally contractible or something like that, but probably I'm not completely, maybe paracompact, or I don't know the precise assumptions, so I don't want to... okay, maybe I could give one or two other examples of derived functors, which are of interest and which are in fact related to Étale cohomology. So another example, take G be a group, C the category of G modules, I mean an abelian groups with a G action, and F the functor which sends M to the set of fixed points, to mg, which is the set of m in m, g of m is equal to m for every j in g. Then it is also left exact. And its derived functor do exist also. Functors are there is a general theory which is called cohomology of groups. And those are precisely, it can be described in plenty of different manners, but one of them is to describe it as hi of G. And those groups can be explicitly computed using cocycles, but it's for H1 or H2 it's okay. After that it's completely awful, but there is an explicit description by cocycles. And now there is also a continuous version of that. There is a continuous version of that. Maybe not only for every topological group, but I'm not sure that for any topological group that the derived functor will always exist or something like that. But in the case I mentioned, I'm sure it does. Continuous version of that fact. You replace G, take G, a profinite group. It means that G is a projective limit of Gi, which are finite groups. Then G will be a compact and totally disconnected topological group, finite groups. And now you take C category of discrete G modules. It means G modules with open stabilizers. And this category, then one can do the same. Look at this functor. It is left exact. It has derived functor, which can be explicitly described by cocycles. The cocycle here will be the same as here, but with a continuity condition. because one deals with a topological group. And then the same holds. And I give this example because it is related. This example with a profinite group is closely related to Étale cohomology, to Étale cohomology of the spectrum of a field, precisely. And so now, what will be Étale cohomology? I will just give the principal definition of an Étale map, and it will be okay. So now an Étale topology on a scheme or analytic space X will be so the category whose objects are y to x Étale. So to be defined, I will define a class of arrows Étale to be defined, whose objects are those maps, whose arrows are just commutative diagram. You take two objects over x, and then you make you choose an arrow which makes things commute, and this arrow will be automatically Étale. And whose coverings will just be the arrows y to y, everything being taken over x, such that here it's a classical notion of a covering, such that y is set theoretically the union of the image of the images of the y eyes. So what will be very important in that stuff is the notion of an Étale map. After that, the notion of a covering will be classical. It just covers in a set theoretical way. But the point is that we only will deal over a given scheme or analytic space X with Étale arrows. So now I want to give the definition. Yes? For being a covering? Okay. What does it mean? So you have a scheme Y and a family of morphisms from yi to y, and you require, when you look at, so it's a morphism of scheme, but forget all the scheme structure, just you have underlying sets. You look at the image of those maps, and you want that all those images cover y. Now, an Étale covering will just be a family of Étale map whose image covers a given scheme. When we will deal with the cohomology of X, we will fix a scheme or an analytic spaces X and only work with the object equipped with an arrow over X. Okay? And so the definition of an Étale map. So the general intuition a map from y to x Étale at y, I don't give the precise definition, just the intuition, has to be thought as an algebraic analogous of a map, of a continuous map from y to x, inducing a homeomorphism from a neighborhood of y to an open subset of x. So consider this classical topological situation. You have a map which is a local homomorphism on the source. Then the Étale maps is the algebraic analogous of this situation to an open subset of x. So it's a remark. Now I give a second remark, then the definition, and I stop. The second remark is that if x is a C-infinity manifold, and an integer and P1, PR polynomials in T1, TR, same number of variables and of polynomials, with coefficients in C-infinity of x, then let y in x times Rn be the set with a zero locus of the PIs, and assume that y is a point in y at which the Jacobian determinant dt dpi over dtg non-vanishes. Then by the implicit function theorem or local inversion theorem, the map from y to x at small y satisfies this property. Then y to x induces an homeomorphism, the diffeomorphism even, okay, an homeomorphism from a small neighborhood of y with an open subset of x. And so this remark, the general way one should think when one thinks to an Étale map, and this fact will, I hope, will give sufficient motivations for the following definition, which I will end this lecture. I will make the comments and examples tomorrow. So now definition. Let y to x be a morphism of schemes, y in y, x its image. Then this map is said to be Étale at y if there exists an affine neighborhood u equals spec A of small x inside x, a neighborhood, affine or not, it doesn't matter, a neighborhood v of y, say phi, in phi minus 1 of u, and a commutative diagram. You have v, you have u, which is spec A, and here I will take spec A of T1, TR, modulo P1, PR for some PIs. I have V, I have that, I have psi, and then with psi, an open immersion, so it identifies V with an open subset of that, an open immersion, such that the Jacobian determinant, dpi, which is a function, which is a function on this scheme, is invertible, doesn't vanish. Doesn't vanish at C of y. So if you look, it's exactly the scheme theoretic analogous of the preceding situation I just described in differential geometry. And that's a reason why an Étale map can be thought as something which is a nomeomorphism around every point of the source space. Okay, I will make the comment tomorrow, so thank you for your attention.